Hello, ME4056. This is Team 5, Nick Shierley, Connor Sims, and Gavin Williamson, giving our Week 1 IC Engines Lab update presentation. Enjoy. Generative Energy Systems has contracted Burdell Incorporated to perform some experimentations on their internal combustion engine. Unlike true IC engines, their engine uses compressed air to simulate combustion. Our client wants Burdell Inc. to determine the mechanical properties of their engine, be it the torque due to friction, the moment of inertia of the flywheel, or the work the motor provides to the system during any given test. With this experimentation, the team will be able to compare the experimental air work the engine provides to the theoretical air work it would provide in an ideal environment. Once system ID is complete, the client would also like us to provide a control scheme that will produce the most power from the engine. While the system ID of the full engine is a daunting task, several components can be isolated by simply removing the head from the engine. Without a head, the work due to air on the system is completely negated. As seen on the right, this leaves the system with two main sensors, the position sensor and the force transducer. The position sensor will allow the team to track the radial velocity of the system and the top dead center positions by collecting angular position data. The force transducer, with proper calibration, will allow the team to convert collected voltages into torques, which will then be used to find the work of the motor for a given run and the work due to friction of the engine. Calibration is extremely important, as it is the only link between voltage and torque applied by the system. Without good calibration, the data the team collects in lab is essentially useless. An example of a calibration equation can be seen on the right. To create this data, known increments of weight were added to the force transducer and the corresponding voltages were recorded. This gave the team a baseline for how the voltage reading correlates to the torque. It is important to note that calibration will be done every week, as many other research groups use the same equipment as us, and that could cause a change in how the force transducer functions in lab. The first equation shown is the entire energy equation of the system with no modifications. Red lettering indicates values that are directly calculable from the sensor readings, while blue indicates values that need more manipulation before calculation. In the first week, our main goal is to find the experimental moment of inertia of a single flywheel disc and the work due to friction of the motor. With the whole system in place, this is not achievable. Therefore, the head is removed to negate the work due to air. Similarly, it is assumed that the work due to the piston zeroes out, and in a perfect situation, the piston provides nor takes any PV work. This leaves us with the second equation. This equation can then be simplified by acknowledging that the work due to friction is simply the work due to the motor during steady state, as the motor is putting in just enough work to stop the friction from overwhelming the engine in that time period. This leaves a rather simple equation for iFly. It is important to note, however, that the iFly found here is the iFly of the entire system. So while this includes the iFly of a single disk, it is not what the client wants. To isolate the moment of inertia of a single disk, two sets of data were taken. One data set with 4 disks on the flywheel, and another with 1 disk on the flywheel. While separate, these 2 points of data are not useful, but by subtracting them and dividing by the difference in disk count between the 2 runs, you will be left with the experimental moment of inertia of a single disk. Both collected data sets were run at 3 different input voltages: zero point 0.3 volts, zero point 0.6 volts, and finally 0.9 volts. This will not only inform us of how the moment of inertia of a single disk is affected by the input voltage, but also how the friction of our engine is affected by the voltage. This will allow the team to better determine if the client's engine follows a Newtonian, voltage-dependent, or Coulomb, voltage-independent friction model.
These two figures present the angular velocity data and torque data for 0.9 volts input and the full flywheel configuration. The As seen on the figure on the left, the angular velocity is increasing as the motor accelerates and then eventually reaches a steady state velocity. This steady state region is the same on the torque data, which we were able to use earlier calibration equation to turn the voltage from the force transducer into the torque. During the steady state region, the only friction and the motor are producing torque. So we're able to isolate these terms and calculate the amount of friction in the system to create a model from that. In general, as the voltage in the motor was increased, the torque friction increased in magnitude, while the moment of inertia increased with one disk and decreased with 4 flywheel setup. As shown in the graphs on the top right, the magnitude during 0.3 volts, the torque due to friction was positive. These values will be neglected in creating our model for torque to be used in the future because the uncertainty in these 0.3 volts is so high that it cannot reliably be trusted. Additionally, you can see that there is a difference between the experimentally derived iFly values and the theoretical ones. This is due to the theoretical model not accounting for the holes in the disks, which would increase the moment of inertia value. However, this will there is a close enough relationship here that we are still able to use the model, the overall model for characterizing the engine. Certainty of the torque friction values were determined to be much larger than the experimentally determined values. Because of this, we will assume a Coulomb friction model, as current sensing does not indicate a correlation between friction and voltage, as can be seen on our data on the right. The values for the uncertainty and friction, as you can see in the table, are much higher, and we are able to use calculate the uncertainty work values, which we can use to characterize our motor in later weeks.
Hey, so my name is Nick, and I'll be talking about the plans and goals we have as a team. And I'll first start off with week 2. And so because of the system's moment of inertia and the work due to friction will not change, the team can now add the engine head to find the work due to the air of the engine, shown in the equation below. And we plan to create a model to represent each cycle of the engine to determine the work the air provides in each stroke. And we could compare the experimental values to the theoretical values found in fluid and thermodynamic equations that were provided. And here are some of the values we got for the intake, compression stroke, power stroke, and the exhaust. So next I'll talk about the plans and goals we have for week 3. And with all the engine parameters discovered in week 1 and 2, the team can now begin to optimize the operation of the engine. And this will have the team adjusting the air injection timing to best simulate combustion, with the goal of finding the engine control parameters that allowed the engine to produce the largest amount of power. And by finding the optimal controls of the engine, the team will have all the information that the client wants and will be able to create a detailed report of the engine's function. So now I'll talk about the plans and goals of the entire lab. So the overall goal is to determine the parameters and control of the overall system to optimize power generation. And the steps we have to do to complete this goal is first to characterize the mechanical properties of the engine. Next, characterizing the discrepancies between the experimental and theoretical work caused from air. And third is to determine the exchange between the pressurized air and the flywheel for optimal power generation. Thank you.